As I said, today we're going to continue with review. Today we're going to talk about fractions, which is always a good review topic because there are a lot of people that get to this level that still struggle with fractions. I know most of you probably are familiar with the fraction calculator, which is fine. But on the test coming up next Friday, there will be several fraction problems that you'll be required to do without the calculator. So let's go through and make sure we understand how to do those operations by hand. So we're going to start out from the very beginning again, and I apologize for going through the basics. But to understand fractions, we first must understand what it means. We talked on Monday about a fraction being a single number with two parts. The count, which is the 3, so what that means is we have 3 of something here, and the name, which is the 4th. So it's like having 3 inches or 3 pounds or 3 x's. We have 3/4. So to start off with, we need to define what it is to have a 4th. And probably the simplest way to do that is to go back to the old elementary school illustration. Pretend that looks like a circle of a pie or a pizza, however you want to think of it. Fourths mean that one whole object gets cut into 4 equal pieces. Or you could think of it the other way, of it takes 4 of these pieces to make one whole object. Now the 3 means that we have 3 of those pieces. So a really quick visual on the amount that we have. The first step in dealing with fractions is being able to rename them. In other words, changing the denominator. Probably the simplest way using this illustration to rename a fraction would be to take each of those pieces and cut them into equal pieces. So if I take each piece and cut them into 3 equal pieces, pretend these look equal. Now, how many total pieces do I have in that pizza, if it were a full pizza? Well, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces. It took 4 pieces to make a whole thing before. You cut each of those into 3, so 4 times 3 makes 12. How many pieces do we actually have? Well, there's 9. We had 3. We cut each of them into 3 equal pieces. 3 times 3 is 9. So we now have 9/12 of a pizza. Do we have any more or less than what we did before? No, we have exactly the same amount. So even though they look different, the 3/4 and the 9/12 are exactly the same amount. And as you guys all know, you can rename any fraction by simply multiplying the numerator and the denominator by the same number. The key is just knowing what number to multiply by. So let's say I want to turn this into 40/5. I have to ask, what do I multiply 5 by to get 45? 9. So I do 2 times 9 is 18. So 18/45 is equivalent to 2/5. We can go the other direction as well. We have 48/60. Now you guys have all been taught that we just do the opposite. You can divide the top and bottom by the same number to reduce it. Here, if we look at that, both of those numbers can be divided by what? Real talkative group today. What can we divide both of those by? 12. There we go. Somebody heard somebody say 6. That would have worked as well. You could divide by 6. You would have 8/12 or 8/10, and you'd have to divide by 2 again. Either way, you're going to end up at 4/5. What we're really doing there is we're canceling out common factors. In math, factoring is actually one of the most powerful tools that we have. If I were to prime factor 48, it's 2 times 2 times 2 times 2 times 3. If I were to prime factor 60, it's 2 times 2 times 3 times 5. When I'm reducing a fraction, all I am doing is canceling out common factors. I can cancel out a 2, another 2, and a 3. And what's left is 2 times 2 is 4/5. Now the numerical fractions, it's just as easy to just divide by whatever we see we can divide them both by. But if we get into algebraic fractions like 12x squared y to the 8th over 16x to the 5th y to the 3rd. Being able to use that factoring helps us to reduce them. Now, many of you have probably reduced these by subtracting powers, which is wonderful. That's the shortcut. But it all comes from factoring. I need to learn to use smaller powers so I don't have to write out so much. So anyway, we cancel out 2's and another set of 2's. We're left with 3 and 2 times 2, or 3 over 4 for the numbers. For the variables, we can cancel out an x and another x. We're left with x to the 3rd on bottom. Cancel out a y, another y, and a 3rd y, and we're left with 5 of them, so y to the 5th on top. So we get 3y to the 5th over 4x to the 3rd. Well, enough of that. Let's look at something like this. 45/7. When you look at that, you can see the numerator is bigger than the denominator. Many of you know that that's called an improper fraction. Nothing really improper about it. It's just called an improper fraction because the top is bigger than the bottom. What it means, of course, the numerator being bigger than the denominator, is that there's enough pieces there to make a whole object. In fact, there's enough pieces there to make several whole objects. So the first step is to figure out how many of those whole objects we can make. If you were to divide this on the calculator, 45 divided by 7 is going to give you something like 6.428574143 approximately. That's not terribly helpful. But if we divide it out by hand, we can think of it as being basically just a long division with a remainder. 45 divided by 7 is 6. 6 times 7 is 42. There are 3 left over. So that means that we got 6 whole objects, and there are 3 of those 7ths left over. We can go from that improper fraction into a mixed number like this. Or we can go the other direction from a mixed number into an improper fraction. Let's say we have 4 and 3/5. To make that back into an improper fraction, we have to take these 4 whole objects and break them into pieces. To figure out how many pieces, we look at the denominator. That 5 in the denominator is telling us that each whole object is 5 pieces. So 4 whole objects times 5 pieces is 20. So the 4 whole objects break into 20 pieces. Plus we already had 3 pieces there. So 20 plus 3 is 23/5. Now again, I'm moving through this rather quickly because I know you guys have all seen this before and probably don't necessarily need much of a review. So now that we can rename our fractions, we can look at simple addition and subtraction. 1/4 plus 2/5. Of course, we talked about when we add numbers, you must have the same name, which means we cannot add these fractions the way they are written. We must change them to have the same name, or in common terms, common denominators. Now, there are several processes we can go through to find common denominators. Because of the level you're at, I'm just going to assume you guys can find the common denominators. In fact, what would we use here for the common denominator? 20, there we go. You guys need to try to contain your excitement today. So anyway, we get the common denominator of 20, so we're going to rename them. 4 times 5 makes 20, so we have to do 1 times 5 is 5/20ths. Down here, 5 times 4 makes 20, so 2 times 4 makes 8/20ths. So now 5 plus 8 is 13/20ths. And there it is. Well, we're not going to waste any more time with simple fractions. We're going to jump up to mixed numbers. When we add mixed numbers, like 3 and 1/3 plus 2 5/8. I always set up my additions vertically because to me that's how it makes the most sense. Now I still need a common denominator. The 3 and the 2 won't change. Between the 3 and the 8, my common denominator will be 24. So I'm going to rename the 3 times 8 is 24. 1 times 8 is 8. Down here, 8 times 3 to get 24, so 5 times 3 is 15. And I'm going to add. Now you'll notice I lined up those fractions at the end just like they're the last digit of the number. Because really that's all they are, is the last digit of the number. 8 plus 15 is 23, so that is 23 24ths. 3 plus 2 is 5. It's not always that simple. Sometimes we have to deal with some other things in there. Let's look at this. 4 3/4 plus 7 5/6. So once again, we need common denominators. Now the first one most people see here is 24, but we can actually use 12. It wouldn't be wrong to use 24. We could do that. We just have to do some reducing in our final answer. But it's always easiest if we can use that smallest common denominator, in this case the 12. 4 times 3 makes 12, so 3 times 3 is 9. 6 times 2 makes 12, so 5 times 2 is 10. Now when we go to add 9 twelfths and 10 twelfths, combining the counts, 9 and 10 is 19, keeping the name of 12. We have a problem there. Just like whole numbers, that's bigger than what we can have in the fraction place value. We can split that up into 1 7 twelfths, where we keep the 7 twelfths and we carry the 1. 1 4 is 5, plus 7 is 12. So 12 7 twelfths. Let's do a quick look at subtraction. We'll jump right into subtraction with borrowing. Let's do 5 1/3 minus 3 5/8. So again, we still need common denominators for subtraction, so it'll be 24 in this case. 3 times 8 makes 24, so 1 times 8 is 8. 8 times 3 makes 24, so 5 times 3 is 15. We go to subtract. 8 minus 15 can't be done, so we're going to have to borrow. Borrowing from the 5 makes this a 4. The tricky thing is, what did we borrow? Well, we borrowed one whole object. And one whole object, depending on the denominator, in this case, has 24 pieces. So it's 8 plus 24 makes 32 24ths, is what we now have. So now 32 minus 15 is 17 24ths. And now 4 minus 3 is 1. Anybody have any questions on the borrowing? Anybody want to see another example of that? Okay. Next is multiplication. When we multiply, we end up with, let me do this. Just like with whole numbers, we multiply the counts and then we also multiply the names. In fractions, what that results in is just multiplying straight across. Multiplying the counts would be the 3 times 6 is 18. Multiplying the names would just be 4 times 15 is 60. And of course, at this point, we'd have to reduce. Both of those can be divided by 6 to give me 3/10. Well, some of you might be looking at this asking, why didn't he cross-cancel before he multiplied? What cross-canceling is since we know that this is going to be 3 times 6 over 4 over 15, over 4 times 15, I should say, we could reduce before we multiply. For example, 4 and 6 can both be divided by 2 to give me 2 and 3. 3 and 15 can both be divided by 3 to give me 5 and 1. So now when we multiply, 1 times 3 is 3, and 2 times 5 is 10. We reduce our answer before we multiply instead of having to reduce later. In a problem like this, it's about the same difficulty to reduce it before or after. But we can run into problems like this, where it is significantly more work to multiply that out and reduce it later. 24 35ths, or 24 times 35 would be what? 840. 25 times 36 would be 900. You'd have to reduce that down. But if we do cross-canceling, or cross-multiplying, as it's called by some books, we can see here 24 and 36 can each be divided by 12 to give me 2 and 3. 25 and 35 can be divided by 5 to give me 5 and 7. And now it is 2 times 7 is 14, and 5 times 3 is 15. So 14/15. This would reduce down to 14/15 as well, of course. It'd just take a little more effort to do it. We're not going to waste any time with simple fraction multiplication anymore. We're going to jump into mixed numbers. When we're multiplying with mixed numbers, the process is quite a bit more difficult. For example, 7 1/3 times 4 2/5. Multiplying mixed numbers is actually an extremely difficult process. In fact, if you were to go to a university and find 10 math majors, I would bet you that probably not any of them would be able to show you how to multiply mixed numbers correctly. It's a very tough process. So what we do is we avoid it. And we avoid it by turning them into improper fractions. 7 1/3 will become 7 times 3 is 21 plus 22, or plus 1 is 22/3, times 4 2/5. 4 times 5 is 12, plus 2 is 14/5. And now we can just multiply them like any other fractions. We could cross cancel, but in this case there's nothing to cancel out. 22 times 14 is 308. 3 times 5 is 15. Does that look right? What's that? Oh, this would be 22/5. That's why. Thank you. Yeah, I don't know where I got 12. 4 times 5 is 20. Plus 2 is 22. Thank you. Some days the little hamster doesn't go all the way on the wheel. So it's 22 times 22 is 484 over 15. Now the difficult part of this is reducing this back down into a mixed number. We have the 485 divided by 15. 15 goes into 48 3 times. 3 times 15 is 45. There's 3 left over. Bring down the 5. 15 goes into 35 twice. That's 30. I did that wrong again. That should be 34. Wow. Sorry, folks. 484, not 485. So yeah, it's 35. 15 goes into 34 twice. That's 30. There's 4 left over. So 32 and 4/15. Sorry about that. But anyway, we got to the right answer eventually. Now, just for to settle any curiosities, I'm going to show you how you would multiply these as mixed numbers. You don't need to put this in your notes. I will never test you on it, but it's kind of interesting to know. When you look at multiplying those as mixed numbers, it's kind of like doing 32 times 53. When you do this, you have to do 3 times 2 and 3 times 3, and then 5 times 2 and 5 times 3. Well, same here. Not only does the 2/5 have to multiply the 1/3, which will give you 2/15, but the 2/5 also has to multiply the 7. Well, to multiply a fraction by a whole number, you make the 7 a fraction by doing 7 over 1. So that's 14 over 5, or 2 4/5. Then we move to the 4. 4 times 1/3. 4 over 1 times 1 over 3 is 4 over 3, or 1 1/3. And 4 times 7 is 28. Now we have to combine all those, which means we need common denominators. It's going to be 15, so I'll stay 2/15. This is 2 12/15. 1 5/15, and 28. Adding 2 and 12 is 14, plus 5 is 19/15, which is 1 and 4/15. Keeping the 4/15, carry the 1. 1 and 2 is 3, 4, 12, carry the 1. 32 and 4/15. We get the same answer. Realistically, I'm going to stick with improper fractions. But you can see it is possible to multiply them as mixed numbers. It's just really tedious. Well, let's move on to division. We said over the last couple days that division follows the same rules as multiplication. When we multiplied, we just multiplied straight across. Does that mean we can just divide straight across? If I do 12 divided by 4 is 3, 25 divided by 5 is 5. Is that the right answer? Sure it is. That is the right answer. Can we do that every time? Well, if it works out, we could. It would give us the right answer every time. The problem is we run into things like this. 3/4 divided by 2/3, where the numbers don't come out. 3 divided by 2 doesn't come out to be a nice even whole number like that. So the way we were taught to do this is the first number doesn't change, but instead of dividing by 2/3, we multiply by the reciprocal of 3 over 2. So it's 3 times 3 is 9, 4 times 2 is 8. 9/8 or 1 1/8. So the question is, where did this come from? Where did multiplying by a reciprocal come from? Well, believe it or not, it comes from this. Let's look at that 3/4 divided by 2/3. One of the alternative methods of dividing fractions involved looking at this fraction that you're dividing by, the 2/3. And you would take the numerator times the denominator. 2 times 3 is 6. And you would use that 6 to rename the first number. So 3/4 is going to get renamed by multiplying by 6 on top and bottom. Well, 3 times 6 is 18. 4 times 6 is 24. 18/24 is equivalent to 3/4. It's just been renamed. It looks different. Now we can divide by 2/3. 18 divided by 2 is 9. 24 divided by 3 is 8, which is 1 1/8. So how did we get from this process to multiplying by a reciprocal? Well, it's not as big of a leap as you would think. At some point, somebody looked at this process here, 3/4 times 6 over 6 divided by 2/3. And they realized that no matter what the numbers were involved, if they did this division here first, 6 divided by 2 is 3, 6 divided by 3 is 2. What you always got here was just this fraction flipped over. So they named that a reciprocal, and since multiplication is left, they just defined the division of fractions to be multiplying by the reciprocal of that fraction. And all that was a shortcut to get rid of all these steps in between involving multiplying, renaming the first fraction. So anyway, again, I'm never going to test you on that. I just wanted to show you some math history of where it came from. We're just going to go ahead now and jump into dividing of mixed numbers. So let's say we have 8 2/3 divided by 2 4/5. Well, dividing mixed numbers, since we're going to turn it into multiplication, only makes sense that we would do the same thing we did for multiplication, and that's turning them into improper fractions. So 8 times 3 is 24, plus 2 is 26/3. 2 times 5 is 10, plus 4 is 14/5. Is this multiplication now? No, it's still division. We may have made them into improper fractions, but we have not taken the reciprocal yet. So again, the first fraction stays the same. It's the one we're dividing by that we take the reciprocal of. So that's 14 over 5 becomes 5 over 14, and now it's times. 26 times 5 is 130. 3 times 14 is 42. We could have cross-canceled here, by the way, but nothing cross-cancels. And then, of course, 42 into 130. It goes in there twice. 2 times 42 is 84. Which is 40. Oops, sorry, it goes in there 3 times, not twice. 3 times 42 is 126. With 4 left over. Boy, something doesn't look right there. Oh, apparently it is. Okay, I'm off for some reason today. Sorry about that. I could have cross-canceled with the 26 and the 14, that's why. So anyway, we got 4 over 42, which is 3 and 2/21. Any questions? Okay, well, let's take this a little bit beyond the numbers then. We already looked at reducing fractions with some variables in them. Let's look at working with fractions with some units in them and some variables in them. We may end up, especially in medical math, we may end up with things that are look like this. 28 milliliters per 5 minutes. And when we're working with a fraction like that, let's say we need to multiply by 30 minutes. So we make that a fraction is 30 over 1. Well, when we're working with fractions, the units can be involved in the calculation just like the numbers can. As we saw with reducing the fractions with variables, we can also reduce with units. Cross-canceling, not only can we cross-cancel the 5 and 30, both are divisible by 5 to give me 1 and 6, but we can also cross-cancel the minutes, and those are gone. So now this is 28 milliliters times 6, which is 168 milliliters, over 1 times 1 is 1. So that's just 168 milliliters. This process is just a very basic introduction to something called dimensional analysis. When we start talking about our dosage calculations, there are dosage calculation formulas that can be used, but you have to memorize them and they don't work for every situation. There's different formulas for different situations. Dimensional analysis, which involves just looking at these units and putting numbers in the appropriate spot to cancel out units or change units when necessary, the calculations then describe themselves by looking at those dimensions. When you get into physics or chemistry, dimensional analysis is a big thing. If the units don't work out, then something is wrong in your formula or in your calculation. Another one that might be very common is we might have, let's say, 6 milliliters per 1 minute as a fraction. And if you're setting up an IV, your IVs, depending on whether you're using an infuser or a manual IV, can't be set up in milliliters. You sometimes have to set them up as drops. So if you have a drop factor that says that there are 12 drops, now the abbreviation in medicine for drops is GTT per milliliter. What that means is 12 drops per 1 milliliter. We can set up our calculation then. If we're getting rid of milliliters, the milliliters have to go on bottom. The drops will go on top, 12 drops per 1 milliliter. And now the units take part in the calculation. The milliliters cancel out. 6 times 12 drops is 72 drops. 1 minute times 1 is 1 minute. So that's 72 drops in 1 minute, or 72 drops per minute. So that dimensional analysis is quite a powerful tool when working with dimension numbers with units on them, because it actually will tell us not only how to do the calculation in the first place, but at the very least when we're done, it allows us to check our answer to make sure that the numbers we've used can be used in that way. Any questions? Okay, once again, we're a little bit early. We have 10 minutes left, but I'm going to go ahead and call it a day there. The stuff for you guys to work on that deals with this is on page 18 through 21 in your books, numbers 1 through 97, the odds. Now again, that's a lot of problems. I realize that is 49 problems. I don't expect you guys to do all of them. Do some of the first few and then skip ahead to the more difficult ones if those are going well. If you have problems, of course, go back and do more of the easy ones and make sure you have it. With that, I will give you the last 9 minutes here to work on homework if you wish. Otherwise, you have a great weekend, and we'll see you on Monday.